In this online lecture, we are going to study about solubility, KSP, and common ion effect. First, we'll look into solubility. So, solubility, it is associated with salts. When we go ahead and try to dissolve any salt, so there are two possibilities, whether it will be soluble or it would be insoluble, right? So let's say our solvent is water. So water soluble salts are those which will dissociate and interact with water. So for example, I have NaCl. It will dissociate means it will dissociate into Na positive and Cl negative. Okay, so I will have these ions, and then let's say these are those ions, and then you have water over here. These ions can go ahead and interact with water as well. However, there is another category. Some salts will not be soluble in water, they will be insoluble. That means they will not dissolve in water. Okay, so they will stay as it is, they will stay intact. Okay, and what will happen? They will settle down. Okay, at the bottom, and we refer to that as precipitate. Okay, so insoluble salts, what they do, they precipitate, they settle at the bottom, and they are not part of the solution anymore. Now, what is next? However, these are two extreme boundaries which we are talking about, soluble and insoluble. However, in between these two boundaries of soluble and insoluble, there lies a category which we call as moderately soluble salts, okay, or weakly soluble salts. So any salt, when we say it is insoluble, however, let me show you next. What we want to see here, this is kind of uh, overlooking into some things. When we say it is insoluble, however, a slight amount of that salt is still soluble. Okay, it is still available for the for interaction, or it is available in the form of ions. For example, here AgI, it is very weak, weakly dissolved as salt here. So what will happen, AJ? So most of it, let's say 95% of it will settle down at the bottom. So what will happen? Only 5% of the ions you will find here in the water. Okay. So even if there is slight solubility, so there is some solubility, right? So if, even insoluble compounds will dissolve to a small degree. Okay. So there will be some degree to which even insoluble salts will be found in the dissociated form, and they will be dissolving here, in even if that amount is very less. So how do we check that? What is the mathematical measure? How do we come to know what is the mathematical term related to find that? So KSP is solubility product. So solubility product, this KSP is a term that would give you insight or will help you to determine the molar solubility of the salt. So for example, let's see here, I have the salt here, AgI, which I was talking. Okay, it exists in the equilibrium between as Ag positive and I negative ions. It is back and forth. And so, what is KSP? KSP is equilibrium. K is the equilibrium constant, and as we already know from our previous knowledge, the equilibrium constant, it is the multiplication of the concentration of the products. What are the products here? Ag ion and I negative ion. And what do I have over here at the bottom? Ag solid, okay, divided by the reactants, the concentration of the reactants. However, this is in solid form, so as you know already, at in equilibrium constant expressions, we don't include solids as well as liquids. They are not allowed. Okay, so you can emit this, and when you will emit this, so what will happen? So you will be left with only this. So since this equilibrium constant is associated with the solubility, so we called it as KSP, or the solubility product. Now moving on, this is my expression here of KSP, and for AgI, it can be as low as 10 to the power minus 50. Okay, it has been found. It is this small. So 10 to the power negative 50 is quite a very small number. However, it is still there. 10 to the power minus 50 is a number. So we will say that even though it is very small, but still some extent is dissolved in the water. So what we want to learn from here is also one another thing, that smaller the KSP, lower will be the solubility. So if KSP value is higher, that means that salt is more soluble in the solvent. Okay. Now moving on, let us go ahead and do some questions here, and let's try to write some KSP expressions. Let's go ahead and try to learn how to write the KSP expressions for some equilibrium reactions. So for example, here CaCO3 is dissociating into Ca2 positive and carbonate 2 negative. So it would be the KSP. So you know that you will write the multiplication of the concentration of the products. This is your one of the product. This is another product. I went ahead and write that. These are equal so these are allowed. However, in the denominator you have reactants, but here you will not include reactant because it is in the solid form. So this is the KSP value. Similarly, you have MgOH twice. It will dissociate into Mg2 positive and hydroxyl ion. So why do I put 2 here? Because hydroxide ions are 2 here, and so you need to balance, you put 2 here. Now Mg is fine, it is balanced on both sides. So what would be KSP? So you will include these two, the product of these two. So Mg2 positive raised to power its stoichiometric coefficient, and OH negative raised to power its stoichiometric coefficient. So whatever is on front, so it will be raised to that power, and then again denominator there will be nothing because the reactant is in the solid form. Now moving on, let's do the next one. Ca5PO4 thrice OH. Okay, so this will dissociate into Ca2 positive, PO4 3 negative, and hydroxide ion. Now if you go ahead and check, so calcium is 5 on this side, so I have to put 5 on this side to balance the calcium on both sides. PO4 is 3 here, so you will have to put 3 here, and OH is 1 here. So this OH is also 1. Okay. Now what would be the KSP? It will be the product of Ca2 positive, PO4 3 negative, and O hydroxide ion. Ca2 positive raised to the power 5, PO4 3 negative raised to the power 3, and OH raised to the power 1. Right. So this is your KSP value. So this is just on the side I've discussed here the different equilibrium constant expressions which we have done in our previous online lectures. We have learned about KW, okay, so in which we reacted two water molecules, and what happened, hydroxide ion and your hydronium ion was produced. Okay, so now this is the KW, the equilibrium constant expression for the water molecules in equilibrium with these hydroxide ion and hydronium ion. So it looks like this, and again water is in liquid form, so you will not write anything in the denominator. So similarly you have K, Kb in case of you have acids and bases. Now moving on, we learned just about KSP, how to write the equilibrium constant expression. Now let's try to do some questions. Now, why we are interested from KSP value, we can go ahead and find the ionic concentration. So, for example, you have this question: if Mg2 positive, its concentration is given 3.7 into 10 to the power negative 3. You have to find its KSP value. Okay, so this is your the equilibrium reaction which is given here, the equilibrium expression. MgOH twice, it's dissociating into Mg2 positive ions and hydroxide ions. So what is happening here? So if you see Mg is 1 on both sides, so I just put 1 here, or you can ignore that as well. It's just for the understanding purposes. OH is twice here, it's 2 here as well. So the things are balanced, okay, on both sides. So what is given here is this thing. So Mg ion concentration, it's how much? 3.7. So if you see here in this solution, okay, so Mg is 1, and if Mg is 1, then hydroxide is twice, okay. If this is 1, this is 2. If this is 3.7, it is 2 into 3.7, right? So this is how we can make use of the stoichiometric coefficients to find the concentration of the unknown, which is hydroxide ion over here. So I have the concentrations over here. 3.74 mg. 2 into 3.7, that would be 7.4 into 10 to the power negative 3. So for the KSP value, which I need to find here, you have to find the KSP in this, for this MgOH twice. So concentrations I will go ahead and put here for Mg, and then 7.4 for the OH, and then you'll raise it to the power 2, okay, and then you'll just go ahead and calculate. This will be your answer, okay. Now moving on, we have this next question, in which you want to find the molar solubility, okay. The molar solubility, that means you want to find the moles per liter, which is the concentration, okay. So concentration of the ions. So CuBr, now it's the other way around question. KSP is given. Now you want to find its molar solubility. So what we're going to do here, we will write the equilibrium expression for CuBr. CuBr will be disintegrating or dissociating into Cu plus and Br negative. Okay. Then we will write the KSP expression, which will be multiplication of this and this, Cu positive and Br negative. And what next we have? Now to find the concentration of the Cu positive. So we will make use of the ice table. What is ice table? So it means the initial concentration, the change which is happening during the reaction, and the concentration at equilibrium. Okay, so whatever we have on the reactant side, I have CuBr. On the product I have Cu positive and Br negative. So I don't need to worry about CuBr. Okay, so initially the products were zero. Okay, at initial there were no products, there were just CuBr. Let's say what change happened here. Let's say X got dissociated over here, and X is formed, and then X is formed because it's 1 and 1, so they're in stoichiometric ratio of 1 is to 1. So what will be the concentration at equilibrium? So 0 plus X, it would give you X here, 0 plus X, it would give you X here. So what we will do, we will go ahead and put this in our KSP expression. What was our KSP expression? I'm just going to write it here. It was like this. Concentration of Cu positive. What is the concentration of Cu positive? X. Concentration of the Br negative, which is X. What is the KSP value? It was 6.3 into 10 to the power negative 9. Okay. This is equal to, so X into X is equal to X square. So that means X square is equal to 6.3 into 10 to the power negative 9. So X would be equal to square root of this number, 6.3 into 10 to the power minus 9. So you can always go ahead and calculate on the calculator. So this would be your answer. Okay. So this is your molar solubility. That means moles per liter. Now similarly, you have another question. KSP of another salt is given, 8 into 10 to the power negative 6. So you can go ahead and pause the video and also try it on your own. What you have to calculate is its molar solubility. We will follow the same thing. So we will first of all write the KSP expression. KSP expression would involve multiplication of the concentrations of this. So Ca2 positive raised to the power 1, hydroxide ion raised to the power 2. Okay, this you don't need to worry because this is in the solid form. Now KSP value is given. And what you want to do is you want to set up the ice table. Initially there were 0 and 0 products. Let's say if X of this reacted, then how much hydroxide would react? If this is 1, this is 2. If this is X, then this is 2X. Okay, so what will be the equilibrium concentration? X and 2X, right? So let's go ahead and put the numbers here. This is X and this is 2X raised to the power 2, right? This is what we have learned so far. This is X, 2X square will give you 4X square, which will be 4X cube. Okay, so 4X cube is equal to 8 into 10 to the power negative 6. So you divide by 4 on both sides, okay, and then what you're left is on the left side is 2 into 10 to the power negative 6 equal to X cube. You take the cube root on both sides, and this is your answer. 1.3 into 10 to the power negative, I think it's 2. Now moving on, This was about KSP. Now we want to learn about common ion effect. Okay, so this is an application that is used to produce salts uh, when you want to have precipitates of a salt. This is one of the method. You can go ahead and you make use of this effect to do so. So this is also known as the one of the example application of Le Chatelier's principle. So let's look into this one. So Le Chatelier principle. So let's say you have two reactants A plus B. It converts into these products C plus D. So what does your Le Chatelier principle say? If you go ahead and increase the concentration of A, what would happen? So the equilibrium will adjust in such a way that it will try to neglect or try to oppose the change. Okay. So if you increased something on this side, it will start equilibrium will shift more towards the right. So the forward reaction will take place more and more as compared to the backward reaction because it wants to deal with this rising concentration of A. So it will go in that direction where your A is compensated, which is used in which your A is being used. So in the forward direction, what is happening? A is being used. It is reacting with B and forming C plus D. So it will shift to the other side. If you do on this something on this side, then it will shift to the other side. Now let's see how we can make use of this thing in making precipitates. So let's say again we talk about the salt AgI. It will dissociate into Ag ions and I negative ions. Okay. So let's say the motive is to produce a lot of AgI salt or the precipitate, right? One and the same thing. Now what we will do, let's go ahead and try to increase the concentration of the iodide ion. Now if I increase the concentration of iodide ion, what will happen? It will shift in that direction in which iodide ions are being consumed. So in this direction, iodide ions are being consumed. In this way, equilibrium will try to balance this change which has been done. Okay, it will move towards the backward direction. Okay, so what you can do is you can add a similar salt. For example, you can add Ki. So what is happening when you add Ki? So Ki will dissociate. It will be found in this way. K positive and I negative ions will be found. What was already present? Ag positive and I negative ions were already present. So with the introduction of Ki, iodide ions concentration increase. So this is how I can increase the concentration of one of the ion by adding a similar salt. Now they both contain iodide negative. So that means equilibrium will be forced to shift towards the left hand side. So I'm making a change on the right side. It will shift on the opposite side, that is on the left side. So what is on the left side? AgI. So that means more and more of AgI will be formed and more precipitates you can find by introducing potassium iodide, a similar salt, into the solution. Okay. Now, next is this thing. Let's go ahead and do one problem and try to learn more. Let's say you have this salt here, CDS. It is converting into CD2 positive and sulfide 2 negative. Okay. So KSP of this one is given to be 1 into 10 to the power negative 28. So what you want to calculate is the molar solubility of CDS. Okay. Molar solubility I already explained to you. So what we will do, we will go ahead and write the salt KSP expression. So what is your KSP expression? This is how it looks like for this one, CD2 positive and sulfide 2 negative. Now what is happening here? You add 0.010 mole of CdBr2 is added and then you want to calculate the molar solubility of CDS. So you have the solution over here in which there was CDS and then you introduce CdBr2 and for this solution you want to find molar solubility. Okay. Now let's go ahead and again make a ice table. So in this ice table, we need not worry about the reactant because it's not involved in our calculation. Initially, what is happening? CdBr2 is already here. So how many moles of Cd will be here? 0.010. So initially you had these many moles. You didn't start with 0. You started with 0.010 of Cd2 positive ions. However, sulfide was 0 initially. Now, what is happening here? Let's say the X got formed during the change, and X is formed over here. Now you will find the concentration at equilibrium, which would be, you will go ahead and add them 0.010 plus X and X on this side. So you have your concentration values for Cd2 positive and sulfide. You will go ahead and do that. Put the numbers here. And when one thing you want to know here is this. So X would be very, very small. So you can go ahead and neglect it. Okay. So X values are very, very small. So adding a very, very small number to this one won't affect much your answer. So you can make your life easy and neglect it. Now let's continue the calculation. So I have KSP value, which is 1 into 10 to the power negative 28, which is given. So when you neglected, what is left? 0.010 and X. Now you will go ahead and rearrange the equation to find the value of X, and you will find it 1 into 10 to the power negative 26. Now this is it for the KSP and common line effect.